Okay, this is a quick snapshot of graphing exponential growth and decay. I was lazy and didn't even write out exponential. So here's an example of an exponential function. There's the fundamental relationship. This is my start value. If this is a number of cells, I have 3 cells and they're doubling. This is your growth factor. And then this is your number of cycles. So it kind of depends on how your quantity is growing. What are the cycles? Is it years? Is it months? Is it number of half-lives? Things like that. So if I want to graph an exponential growth or decay function, these numbers work pretty well. If I plug in -1 for x, I'm going to have 3 times 2 to the -1, which we all know now means 3 over 2. 2 to the -1 is 1/2. 0, anything to the 0 is 1. So 2 to the 0 is 1. 3 times 1 is 3. 2 to the 1 is 2. 3 times 2 is 6. 2 squared is 4, 12. So at -1, I'm over here at 1.5. At 0, I'm at 3. At 1, I'm at 6. And at 2, I'm at 12. And the key thing here is that where is this going to go as x goes to negative? As x goes to infinity, we know this is just going to grow and grow and grow and grow. As we go backwards, what do you think is going to happen to this graph? And here's my question. Is there any number that you could put in there that would make this quantity negative? So is this ever going to cross the x-axis? Think of a number you could put in there that would make this whole thing negative. And your answer is there isn't anything. Because even if this number is a really big negative number, remember, so if I have 3 times 2 to the -10th, that's just 3 over 2 to the 10th, which we know is a really small number. So what happens as x gets smaller and smaller and smaller and smaller? The value of my function goes to 0. So I do have a horizontal asymptote here at y equals 0. Okay, what about these? Here's our old friends shifting and scaling, and yet to some degree this number out front is kind of like a stretch. This initial value, again, this graph is going to go right 4 and up 1, so right away we know we have a horizontal asymptote at y equals 1. This is going to never cross the line y equals 1. So x prime, y prime, those are ways to indicate a transformation. So if I'm going to go right 4, this new number is going to be 3. And if I'm going to go up 1, instead of 3 halves, I'll have 5 halves. And if I'm going to go right 4, my new number is going to be 4. And I'm going to go up 1, 4. And if I go right 4, my new x value is going to be 5, and my new y value is going to be 7, my new x value is going to be 6, and my new y value is going to be 13. So at -1, I'm up here at, at 3, I'm around 5 halves. At 4, I'm at 4, at 5, I'm at 7, at 6, I'm at 13. So again, this is going to look something like that. So this graph just got shifted to the right 4. Every point went right 4 and up 1. Right 4, up 1. Right 4, up 1. Anyway, so that's exponential growth. Make a simple table of values. You wouldn't have to do it this way. You could, put this function in your calculator, make a table of values, whatever. But I want you to continue to see this idea of shifting and scaling. What about if we have decay? So again, now this is a growth factor, except what do you notice? It's getting cut in half. So if I start with 10 grams of carbon and every year I lose half of them, what happens? Well, again, negative 1 means 10 times 1/2 to the negative 1, and 1/2 to the negative 1 means 2. So this is going to be 20. Anything into the 0 is 1. 10 times 1 is 10. And then 1/2 to the 1 is 1/2 times 10 is 5. And 1/4 of 10, I don't know what's 10 over 4. 2.5? So in this case, yeah, at negative 1, I'm up here at 20. At 0, I'm at 10. At 1, I'm at 5. And at 2, I'm half of that. So this is what exponential decay looks like. Another transformation that can happen is everything just becomes negative. So all these values up here would just become negative. So it would be the result of that. I'd get a reflection over the x-axis, and it would look like this. That can happen with exponential growth too. This, if I put a negative out front here, would just get reflected. So we're familiar with that as well. Incidentally, if you just see y equals 3 times x, what's your start value? What did we start with? That number 1 is essentially out front there. And then in 7.1, you also saw the compounded interest formula. And if I start with $100 and my interest rate is 3%, and it gets compounded monthly for 5 years. So here's my principal, what I started with. My rate is 3%, expressed as a rate. Monthly, that means n is 12, and 5 years, t equals 5. So you just plug all those things in. If you have a new operating system, when you go into the exponent, you can just do 12 times 5. If you have an older operating system, you need to remember to put that in parentheses. If you caret 12 times 5, you need to put it in parentheses. Otherwise, it'll raise it to the 12th and then multiply. Your calculator will follow order of operations. So at the end of those 5 years, you have earned a whopping $16. That's because you only had $100 in there. And 3% is actually not a bad rate right now. You're not going to find that in a savings account. Okay, so that was a quick intro into 7.1 and 7.2. I think between that and the study guides or the textbook, you should be able to tackle those.